coming. Before the main parts of our topic, I want to say thanks to Nikita and Aldis for inviting me to Riga. I haven't been here for a long time, and it's very nice to visit the city again. So, my name is Denis, and I'm working as a data scientist at a company called Data Labs from Minsk, Belarus. It's better to say Belarus, not Belarusian. Today we'll speak about convolutional neural networks, and especially about convolutional neural networks in the context of generative modeling. And during the next, I suppose, 45 minutes, we'll discuss the following things. First, we'll try to find differences between discriminative and generative modeling. Then a short introduction to convolutional neural networks. And then we'll have a lot of fun with training network to fool another network. Then we'll make a step further and try to build a generative model to produce photorealistic images. And there are a lot of difficulties here, so we'll try to avoid them, some kinds. And finally, we'll speak about such an interesting idea, which is called Generative Adversarial Network, and how we can use it not just to have fun, but to solve some real problems. And my main goal for today is, just give a brief overview of the topic, so I could be maybe informal or inaccurate in some formulas, but who cares? We just want to have fun with neural networks, so let's start. Speaking about data modeling process in general, if you want to do something with data, often you want whether to predict something or to investigate how the data was generated. The first type of models, when you want to predict, is about discriminative modeling. And the goal is to find a separate surface between classes, or in mathematical terms, you often want to approximate a posterior conditional distribution of labels y with respect of some features x and parameters theta. An example of such kind of models is logistic regression and all the things you usually use in machine learning, gradient boosting, all models from scikit-learn. Most of the deep learning, successive deep learning models, they try to predict something. When we're speaking about generative model, our goal is to recover the joint distribution of labels and features, not the conditional, but joint. So if you have generative model, you can apply the bias rule, and then you can receive this posterior distribution. So if you have generative model, it's not a problem to build a discriminative model, usually. For example, such popular class Sapphire as naive bias works like this. But at the same time, if you have generative model, you can do very, very funny things. For example, you can construct some sampling procedure and sample new data points from your distribution, which will be very likely to appear in real life. Obviously, this kind of task is much harder than this one, and that's why the most of success is concentrated here. But today we will speak a little bit about discriminative model, and then how we can build generative model if we have discriminative, not without using this, bias rule and so on. On this slide, you can just see the illustration of things I have been talking about. In discriminative modeling, you try to predict, so you are searching for decision boundary, but in generative modeling, you try to approximate the whole distribution of data. So, in one slide, this is a difference between them. The second thing I want to talk about before we'll try to generate something interesting is convolutional neural networks. Are you familiar with neural networks, with convolutional neural networks? Mm-hmm. Anyway, yeah. So just for recap, what is the main idea? Main idea is so. Every convolutional neural networks, practically every, consists of two basic operations. One operation is discrete two-dimensional convolution, and the second is subsampling or pooling. With this basic block, with these two basic blocks, you can build a very successive architecture. So we will try to figure out what is convolution and what is pooling, and then we'll go further. So to deconvolution, suppose that we have an image which is represented as a matrix of integers, and then we have another matrix which is usually much smaller. Here is 3 by 3. This is called the convolutional kernel. And what we want to do is first we place our kernel to the top left corner. Then we multiply element-wise all elements here, and then find this summation. And this summation is a destination. So we receive the destination pixel from the source pixels convolved with the kernel. Then we make a step to the right and calculate the next pixel, then step to the right and the next pixel. Then we'll go a step down and so on, and we'll stop when we'll reach the right bottom corner. This operation is called, what we've just done, we convolved image with the filter and achieved the observation map. In convolutional neural networks, usually you have a lot of, you operate with convolutional layers. Convolutional layer consists of many filters of the same size, but with different weights. So if you convolve this image with a convolutional layer with, for example, 64 convolutions, then the activation map will be sized the same as the image, but 64 channels. And usually you have 3 channels in your input image because you're working with RGB channels, yes. And it's quite popular technique in traditional computer vision. So you can take some photo, choose the convolutional kernel with such weights and achieve edge detector. Then such kernel can help make your image more sharper. This one is a Gaussian blur. So what we can see that kernels could have different sizes, 3 by 3, 5 by 5, different weights, and the whole magic of convolution is hidden in weights. In these examples were designed by engineers, by people, and it's very hard to find some specific kernel for your specific task. And the main idea behind convolutional neural networks is okay. I don't want to think about. I don't want to think a lot. That's why I'll find these kernels just from data. I have a lot of data. Okay, let's try to find the good weights from data. And so we're aiming to find weights of filters based only on data, and also want to achieve some invariance to small distortions of images. It can be shown that if you have some specified network architecture, you only specify the blocks, the sizes of convolution, the stride, it is a step which you move your sliding window, and how many convolutions you have and so on, but you do not specify weights. And if you have training data and some loss function, suppose cross entropy for classification tasks, then you can optimize your weights of filters to minimize the error on your training data. It's quite nice. It's quite nice because convolution is a differential operation, so it's not a problem to calculate gradient, and you often use then you can use any gradient-based optimization, but usually you have a lot of parameters in convolutional networks, about maybe 15 million. That's why the second-order methods based on Newton method, they usually don't work there. That's why we usually use gradient descent and some variations of gradient descent to scale this optimization problem on really big data. Okay, the next operation is called spatial subsampling or just pooling. It is the second main building block for convolutional neural networks, and the good news that it doesn't have any trainable parameters. And what it really does, it just reduces convolution activation maps in the spatial dimension. You have the same number of channels, but your activation maps became smaller in the spatial dimensions. And how it actually works? Is the same. You have to specify the size of your pooling. For example, here we have, I suppose, 2 by 2 pooling with the stride 2. Stride is the step which we will do in the spatial dimensions. And then you should specify some aggregation function which you will use to summarize the values inside your sliding window. So the results of max pooling is the maximum pooling with 2 by 2 filter and stride 2 for this kind of activation map is so. So for this part we have 6 as maximum, here we have 8 as maximum, 3, 4 and so on. And such thing makes your filters, in general makes your network more invariant to small distortions, because if we'll have here 4, 4, 5, 6, then maximum is also 6. You can use average of these numbers or minimum in some tasks, but most common used kind of pooling is max pooling, because it tends to work better in practice. And a very good thing about why people like to use pooling is because it reduces the spatial dimension. For this example, we also have activation map of, suppose, 224 pixels by 224 pixels by 64 channels, and we apply max pooling 2 by 2 with stride 2, and we'll have 4 times less activation map. It means that we'll have 4 times less computations, 4 times less weights on the subsequent layers, and so As an alternative, you can use 2D convolution, but use strides greater than 1. It's quite common too. Okay, so that's all. The common, the typical formula for convolutional neural network is so we have some input image, for example, three-channel image RGB. Then you have some convolution layer with some predefined filters, with filters of predefined size, and number is also predefined, but weights is trainable. Then you have some, it's called rectified linear unit. It's just a non-linearity added on top of convolutions because you want to make a decision boundary very non-linear to solve your task as accurate as you can. Then you repeat this block for maybe n times. It is your hyperparameter. Maybe you want pulling them, maybe you want to, I suppose you want to make your architecture really deep, that's why you want to repeat this block maybe 2, 3 or 4 times. Then if you're solving the classification task, you may add the fully connected layer and so on. It's very common formula. We have some variations nowadays. ResNet, on Inception by Google. They also work in the same manner, but they have some tricks to improve gradient propagation and some techniques to reduce the amount of parameters in your filters, because usually you have a lot of parameters here. About tendencies, sometimes people nowadays people don't like to add fully connected layers in your network, even if you're solving classification tests, because as we will see 2 slides further, the most of parameters usually concentrated there. So we have tendency for fully convolutional networks, and I suppose that both ResNet and Inception are fully convolutional. The most known example of realization of this formula is so-called VGG family, VGG 16 on this slide. As I remember, maybe 5 or 6 years ago, VGG 16 and 19 were the state of the art in the many tasks in computer vision, image classification, and object detection, and so on. As you can see, it's just what we're speaking about. We have image of such size. Then we apply 2 layers of convolutions, so we have tensor of such dimensions. Then we apply the pooling layer, and we reduce our spatial dimension, and then we apply convolutions again, and finally we'll have the tensor of size 7 by 7 by 512, and then we add the fully connected layer with 1096 neurons, and finally we have a classification on 1000 classes, because usually it trains on the ImageNet. We'll talk about this later. The same picture, but I've got it from Keras. Keras is a quite popular framework for fast deep learning. I mean for fast experiments. Not fast computations, fast experiments. And as you can see, the most VGG 16 has, as I remember, about 100 and maybe 30 million parameters, and practically the most part of them is concentrated on the first fully connected layer. It is a place when we give our last activation map, then we flatten them, so we have 7 by 7 by 512 features, and then we add the fully connected layer with such amount of neurons, so we have a lot of parameters there, and that's why people tend not to use convolutional fully connected layers, even in classification tasks. So, why people usually want convolutional neural networks to be deep? It can be shown empirically that each layer works on a different level of abstraction. You know, the first layers they work directly with the image pixels, and they extract some primitives, you know, like lines or blobs or gradients between different colors. The deeper layer, they form textures. The more deep layers, they try to extract some abstract features, like, you know, maybe it is a clock and the face of a dog, and so on. It is, I suppose it is a generated example, but it is this is a real example from this article. As you can see, we have low-level features, gradients, blobs, lines. Then we have some geometry, maybe circle, or hard to say what is it. But then we'll have wheel of a car, and so on, so on. And for computer, it's very hard to work with the raw pixels. And the convolutional neural network can train a very good feature extractor directly from data, and in the final representation, your image will be coded as, you know, okay, here's something that has a wheel and something yellow. Suppose that it is a car. So that's why we want our architectures to be deep. We talked a little bit about ImageNet. ImageNet is a very common competition in computer vision, and one of the tasks is image classification. You have 1 million images and 1,000 classes, and your goal is to do your best. The metric here is accuracy, as we can see. VGG16, VGG19, ResNets, Inception. It's top one error, and we see that it's quite successful models, and this model is very successful. On the right side, we can see the very nice figure. Here we have accuracy. Here we have amount of operations in GOPS, and here the size of circle is amount of parameters. As you can see, VGG16 have a lot of parameters, and for example, Inception have much less, but have a better accuracy. So, but Inception is a much deeper architecture, and ResNet is much deeper architecture. And despite the fact that they has small amount of parameters, they are more powerful models. So it was some recap of basic ideas of convolutional neural networks, but we're here to build a generative model. And what we know a priori, that the joint distribution of image pixels is very complex, and it is not possible, you know, to fit any analytical model to it, like, you know, multivariate Gaussian or something like that. So classical methods don't work then. But okay, if we want to generate something, let me introduce this trick. We know how to sample from multivariate Gaussian. For simplicity, let's sample from multivariate Gaussian, where each component has standard Gaussian distribution. So it's very simple to sample such vector. And as we like neural networks and we don't know what to do, how to approximate this distribution, but we have data, we'll look for parametric transformation of this vector G. So the transformation G of Z will return an image, and what we want that the distribution of these images, pixels of these images should be close to to distribution of real images. So general idea that we are searching for parametric transformation. In this transformation, it's a neural network. We can define the structure, but we don't know the parameters. So if we have some data, we can then we can optimize our parameters. And actually, we'll try to do this right now. How to build, how to compare whether this distribution is close to distribution of real examples if we don't know how this distribution looks like. Idea is quite simple. We have strong discriminative models. We've just talked about VGG and ResNet, and weights of this network trains on ImageNet available. For example, this link is for Keras, as I suppose. And if you have such model, then for every image X you can get the D of X. It is a vector of probabilities, which is sum to 1. And for example, the class number 441 is a glass of beer, and class 968 is a cup of coffee, I suppose, or something like that. Okay, so it's great. The trick is let's look for G of Z so that D of G of Z is close to predefined distribution. So we try to, in simple words, we try to find such transformation that will take our random noise, then apply some magic, and in the result we'll have image which our strong discriminator should classify like a real example. And what you should do to generate images for class cup? Okay, you choose some discriminator, then you sample noise from Montserrat Gaussian, and then you define some architecture for this transformation. And what you want is to D of G of Z be generates a distribution where the whole probability mass is concentrated on number. Sorry, it doesn't work. On number 968 because we want to produce cups. Yes. So we're solving a classification problem. That's why we're using cross entropy. But because here we have all classes 0, we have the only one part of loss which is connected with our cup, and we minimize it with theta, and looks very nice. So this is how it should work. We sample something from Gaussian, then have some transformations, and finally we'll have 64 by 64 by 3 tensor, which we can think about as image, and then we want this tensor to be classified like a cup. So let's try. I've defined some kinds of architecture, and as I said before the start of the optimization, all the weights in the network, they are initialized at random, so it's not so when we So when we feed forward our vectors to the network, we get a random image. It's okay. And this there is top 5 probabilities extracted with VGG16, and you know that it looks like they are not. Model is not confident what is this because it's just random. But on the left, we'll take a cup, and the VGG16 will say that with probability about 0.46, it's a cup. It's so strange because I have standardized this image, subtracted mean and divided by standard deviation for each color channel. It's a very common preprocessing technique to improve your way how you train your network. But then look at magic. After training the transformation, we have random noise classified as a cup, more confident than real image. And the next, it's one sampling, there's another sampling, and we also have there that's random noise where classified as a cup, more confident than a real one. So you may think that it is a problem of architecture, but let's take ResNet and try the same. You see, ResNet says that this cup with quite a big probability, and this is quite looks like random for ResNet. Then we'll solve our optimization problem, and everything is even funner because it is a cup with probability 1, and it is a cup with probability 1. So we have bad news. Why so? Let me answer the question: how many images of such shape exists? It's a very big number, and the problem is that you are training your networks only on the photorealistic images taken from real life, and in real life we have no such images. And the problem here is in the statement. The issue is that here is that in the statement of our problem, I'll show what we want from our model. We want only a predefined classification was required, but we did not require any naturalness from our G of Z of theta. And because this number is so big, with a high probability, you can find image which will look like noise and classify it like any class you want. And it is a and we'll have some fun again. We'll fix our image. Okay, we'll take this cup, and this cup is classified by discriminator as a cup. Everything's okay. But then we'll try to then we'll define our transformation as our source pixels of this image plus some delta theta, which is unknown. And then what we want to do is to d of g of x be classified like a glass of beer. You know, it's like turn water into wine, but turn cups into beers. It's quite nice. We can write some codes in Keras, very little codes, and what we're minimizing, we're maximizing the probability of this full classification, but at the same time we want our destination image looks as much possible as looks as close to cup as it possible. Oh, sorry, this is they're constant alpha, but I've missed this in the formula. What we can do, we can take a cap, then solve this problem. It is theta, and now this is a glass of beer. You know, cup with some noise, glass of beer. We can fool with such technique. We can fool any convolutional neural network. Yes, they are very powerful. They can solve different techniques. But if you have possibility to calculate gradient through this network, then you're in trouble. So it's better to hide your networks. And it's not my personal ideas. It's from this article I've